So the new speaker is Professor IZMESTIEV. So he's from Technical University of Vienna, Austria. Perhaps recently joined this university. Yeah. So it's pleasure to be here, sir. So I request you to please continue your talk. Yeah. Yeah.
Thank you. So, the topic of my lectures is convex sets and mixed volumes and inequalities for mixed volumes. And I start with the basic definitions today. So there will be three parts of the lecture today. So I guess the definition of convex set is known to everybody, but still I want to give it because otherwise I will feel myself not comfortable starting somewhere in the middle. So a definition is set K, which is a subset of Rd, is called convex. If together with any 2 points in this set, it contains also the whole segment between the points. So if for any P and Q in K, one has the segment between P and Q, which is by definition the set of all lambda P plus 1 minus lambda Q, with lambda between 0 and 1. If this is a subset of K as well. So with the picture, of course, that means that if you have 2 points, P, Q, the segment must be inside the body, and something like that is not convex because it is not by definition. There is an alternative definition of that where one takes not only 2 points but any number of points. So alternatively, for any P1 so on Pn in K, so any number of points in K, any convex combination of these points I think I will use the term convex combination later. So what is a convex combination is, it is lambda 1 P1 plus lambda n Pn, where the coefficients satisfy the following. They are non-negative and their sum is equal 1. So any convex combination also belongs to K. So this is a convex combination of 2 points, and that's a generalization to any number of points. So another piece of terminology, well, so one starts with definitions as usual. If you take a convex set which is closed, well, bounded, so that's compact, and also has a non-empty interior, then it is called a convex body. Is a compact convex set, well, subset of Rd. And I have to insert here also convex body in Rd. Is a compact convex subset of Rd with non-empty interior. So this condition on non-empty interior is actually not very important, but it is just there. So it is called. So it is used as a necessary condition for this to be called a convex body. But for example, if you take a triangle in the plane is a convex body in the plane, but triangle in the space is not a convex body in the space because it has an empty interior as a subset of the space. So some examples. First, there are convex polytopes. In RD, so everything is in RD. D is the dimension of my space. Convex polytope is the convex hull of finitely many points. Finitely many points. And by convex hull, so it's similar to the linear hull or a fine hull. By convex hull, we mean the set of all convex combinations of these points. So the set of all convex combinations. Of these points. Okay, so that's easy to imagine. So just take, for example, 4 points in the space, and that will give you a tetrahedron. Or take points, so take vertices of the cube, then the convex hull is the cube itself. But there is an alternative way to see so these polyhedral objects like cube and tetrahedron, and this is by taking a convex, looking at them as convex polyhedra. So a convex polyhedron so this is the intersection of finitely many closed half spaces. Okay. So every convex polytope is also a convex polyhedron. And for example, so if we speak about triangles, then let me make a very, very small picture here. I can view a triangle as the convex hull of 3 points, but I can also view a triangle as the intersection of 3 half spaces, right? So every convex polytope is a convex polyhedron. That's, well, that has to be proved. That's very technical. In the opposite direction, a convex polyhedron is a convex polytope if it is bounded. So the first definition does not allow non-bounded objects, but a convex polyhedron can be just one half space. So I've not write it down, but this is almost equivalent. So if one adds here bounded convex polyhedron, that's the same as a convex polytope. And convex polytopes and polyhedra are, so it's already a very interesting class of objects. So combinatorially and geometrically, but another source of convex sets are, of convex bodies are bodies with smooth boundary. So the region bounded by a hypersurface with non-negative definite second fundamental form is a convex body. Bounded by a hypersurface with the second fundamental form non-negative is a convex body. So a few words about that. So this condition is local, but it implies the global convexity. And that this condition is necessary, it's, well, not difficult to see, because if this form is not non-negatively definite, then so by this indicatrix of Dupin or things like that, so you can see that in the neighborhood of the point you have okay, so again, so actually here the formal proof is quite technical, but I think in the three-dimensional space, the necessity and sufficiency is more or less obvious. So because you must have elliptic points everywhere. If you have a non-elliptic point but a hyperbolic, then this set is not convex. Good. So there are these two classes. One is the polyhedra. The other class is the smooth bodies, or bodies with smooth boundary. But there is also so a huge variety of bodies which are neither smooth nor polyhedral. So take, for example, any infinite subset of the circle and take the convex hull of it. Since the set is infinite, you will have not a polygon but something more wild. And since this set also has some holes or maybe some accumulation points, it will be really something quite nasty. On the other hand, convex bodies are almost everywhere smooth. So the boundary of a convex body is in fact C2 almost everywhere. Almost everywhere. Even the most non-smooth objects, the polyhedra, they are C2 almost everywhere because they are C2 on their faces. Right? So if this is a part of a three-dimensional polytope, then every point here is flat, it is smooth. Only the points on the edges and the vertices are non-smooth. But on the other hand, the most interesting things for polyhedra, they happen at the edges and at the vertices. So if you say it is C2 almost everywhere, therefore we can just study only the smooth theory and everything else can be derived from here, then this is false, because if you study the convex bodies, you also must look at the non-smooth points. Okay. So one last remark in this first part is that convex bodies have a well-defined volume. Convex bodies are measurable. And they are even Jordan measurable. So if you don't need to assume countable additivity, it's enough to have the finite additivity and take the inner measure versus the outer measure, and they will be equal. So the supremum of the volumes of the somehow this step bodies inside is equal to the infimum of the volumes of the bodies outside. And the volume of a convex body in RD I will denote by vol sub d of k. Often I will omit d when it is clear, so what this d is. So convex sets and convex bodies and this volume, these are the main actors in this course. And let us see what interesting things come out of these objects. So the second part today is the Steiner formula. So again, let us define K is always some convex body, and by K sub R, I denote the set of points at distance at most R from K. So the set of all X in RD such that the distance from X to K is less or equal R. For example, if I take a triangle, in the plane. So d is equal to 2. Then this our neighborhood of the triangle. There are these strips along the edges of height r, and there are also circular sectors. So these are the points for which the closest point is one of the vertices. So this body with piecewise smooth boundary is at this R neighborhood. Then the theorem, so which is usually called the Steiner formula, is that the volume of this volume of Kr is a polynomial in R. It is a degree D polynomial in R. So we can write volume sub D of K sub R. This is equal to the sum K from 0 to D a K of K times R to the power K, right? So the coefficients of this polynomial, they depend, of course, on the body K, and but for any body K, there is some collection of coefficients such that the volume is given by this polynomial. So this formula was proved by Steiner in 1840, and at that time people didn't think much about high-dimensional objects, so he looked at three-dimensional bodies, which is already interesting enough. And he looked only at our two special cases. One is when K is a polytope, and the other is when K is smooth. But I will now write this just on the other blackboard. Okay. So namely in these two special cases, so in the polyhedral and in the smooth, and in dimension 3, the coefficients have some very nice form. So then theorem, so which is what Steiner proved. So first, if K is a polytope, then this polytope in R3, the volume of Kr, I will not write volume 3 of Kr. This is equal to volume of K plus R times the area of the boundary of K plus R squared times 1/2 the sum over all E of theta E times L E, and then plus R cube 1/3 the sum over all V of theta V, where I have to explain my notation. So the first sum is over edges. So E is an edge. And theta E is the exterior angle at this edge. So that is the angle between the normals to two faces at E. So, and LE is the length of E. So it is good to try to draw a picture. If the picture will be good, it is good. If not, then we have at least tried. So assume this is a vertex or a polyhedron. The polyhedron lies somewhere there behind the blackboard. So then for this edge, what we are taking the normal to this top face, and here I take the normal to this face, and so when I put them here, then this angle is theta E, and this was the HE. Now V is the vertex, and theta V is again the exterior angle at this vertex, which is in this case angle spanned by the three normals to the faces. Well, there can be more faces at this vertex, so this is the angle spanned by the normals to all faces incident to V. Good. So that's the formula in the polyhedral case, and now I will write the smooth case. For K convex subset in R3, so convex body with smooth boundary, one has the following. The volume of KR is equal to the volume of K plus R times the area of the boundary of K plus R squared times 1/2 the integral over the boundary of K of kappa 1 plus kappa 2. So the integral is taken over the boundary, so integral over the volume element of the boundary, just write the area, and then finally plus 1/3 and plus R cube times 1/3 the integral over the boundary of K, kappa 1 times kappa 2 with respect to the area element. Kappa 1 and kappa 2 are just the principal curvatures of the surface. Right? Can one simplify that formula? So this last one. One can write this not only shorter but also more explicitly. One of the terms here actually does not depend on the body. Which one? Yeah, so that's the integral of the Gauss curvature, and then by Gauss-Bonnet this integral is actually equal 4 pi. Right, so that's the integral, because the product of the principal curvature is the Gauss curvature, and the integral of the Gauss curvature is 4 pi by Gauss-Bonnet theorem. Note that, so just on this place I have written the year 1940, so when Steiner discovered these formulas. Actually Gauss-Bonnet was, I don't know when it was proved, but I guess about at that time. So that was a very modern research 150 years ago. Well, 180 years ago. And this is still very interesting today, as I want to explain. So let us now see how this, yes? So what can be the coefficients of this? Yes, that's, I'm not sure this is answered. I'm not sure it is completely known. But there are questions like, if you know the coefficients, can you say something about the body? And so there are some inequalities which the coefficients must satisfy, and I will speak about these inequalities. But of course, so the coefficients, there are only two of them, so the area and so this strange thing, and so they will determine the body if the body itself belongs to some class, to some three-dimensional class of bodies. For example, so and that can be a good exercise. So take the boxes of, so segment 0 to A times 0 to B times 0 to C, and compute these coefficients. And so compute the coefficients. And think about inequalities which these coefficients must satisfy. So I will come to the coefficients so sometime later again. So let us look how this formula is proved. Actually, for the Hitler case, almost everything is already on this picture, because the other part consists of cylindrical wedges based on the edges, so similar to that picture, but multiplied with a segment. And the volumes of these wedges, they are exactly this term, because each cylindrical wedge, so it's something like this. Each such wedge has the angle theta e here, has the length LE here, and has the radius r. So if you compute the volume of this part, then it will be exactly this. So you have to multiply LE with this part. And then there are such ball sectors, and at the vertices and these sectors of the ball, they have this volume. So our neighborhood is the body itself plus the prisms plus Gauss-Bonnet also for polyhedra, because if you look at this expression, so these angles which are based at the vertices, so as this one that I have drawn here, if you take them at all the vertices and then move them together, then they will form a ball. So in that picture, it's more easy to see in dimension 2. So if I take these 1, 2, and 3 and move them together, then I get a circle subdivided into 3 sectors. The same thing happens in all dimensions. So in dimension 3, when you move these things together, they fill a ball. And this means that this term, which one? So this is also equal to 4 pi, and that's sort of discrete Gauss-Bonnet theorem. Note that the proof of discrete Gauss-Bonnet theorem is very simple. Good. So I wanted also to speak about the proof of the smooth case. I maybe write just one line, so a sketch of the proof for this case. So for this we look again at, well, so there's the volume of K, because Kr contains K. Now we are left with a shell around K. How to compute the volume of a shell? So for this we should find some parameterization of this shell and then compute the volume as we are taught in differential geometry. So for this we take any local parameterization of the surface of the boundary of K. So parameterization so let this be a local parameterization of the boundary of K. Then consider the parameterization capital sigma yes, so where sigma of u v t is equal to small sigma of u v plus t times the normal vector at the point u v, right? So parameterized just by for every point here, I'm going down to the surface, look at what point I am, sigma of uv, and then this distance is and then if we want to compute the volume, so we have to compute the determinant of the Jacobian matrix, and one of the components in computing this determinant is to compute the cross product of capital sigma. So it takes the capital sigma u cross product with so I need to eliminate my formula step by step. Okay, to prove this, it suffices to look at the special case when sigma u and sigma v are the principal curvature directions. So, without loss of generality, sigma u and sigma v are principal curvature directions, and then the formula is easy. And in general case, it follows by substitution of variables.
What is this? Interlude?
Excuse me?
What is written before
without loss of generality. It was maybe faster to write it than, but good that you ask. So without loss of generality, just Okay, and when you have that, then you integrate this over all t from 0 to r and over the surface, and when you integrate, then you see at the term t squared, the product of the principal curvatures appearing, and at the term t, the sum of the principal curvatures appearing, and this yields the formula. Okay, so now, let me summarize what we now proved in the smooth and discrete case. So now for any for K a convex polytope, or smooth convex body, one has the following. The volume of the R neighborhood is equal to the volume of K itself plus R times the area of the boundary plus, and then there are two different formulas. One is, well, R squared is always R squared and 1/2 is always there. But here we have two possibilities. One is the sum of angles times length. The other is the integral of the sum of the principal curvatures. And then there is the last term, which is just R cubed times 4 third of pi. Right, so the Gauss one there. Good. So if one looks at that formula, then one understands why this expression is usually called the total mean curvature of a polyhedron. So 1/2 the sum of theta e L e is total mean curvature of a polytope. Well, that's just giving a name by analogy. But in fact, there are much more serious things happening here. In fact, this expression, so which I will call, I don't know, so I should call it somehow. So this will be called S of K. And we have defined S of K only for polytopes and smooth bodies. In fact, this S of K is continuous with respect to the Hausdorff metric on the space of convex bodies. S, so the function S is continuous on with respect to the Hausdorff metric period. That's another useful abbreviation with respect to. I will speak about Hausdorff metric also next time. Now I just want to present more interesting things. And also why it should be continuous. It should be maybe become more clear tomorrow. But this means that if you take a smooth convex body and take a sequence of polytopes approximating this body, then this expression in terms of angles and lengths will converge to the integral, to this integral. So if Ki tends to K, then S of Ki tends to S of K. And another fact is that So again, the set of all convex bodies is much more bigger than just polytopes and smooth bodies. So for any convex body can be approximated by polytopes, and therefore it is possible to extend this function to the space of all convex bodies. Well, so there one needs to prove some topological details. So why from this continuity it follows that there is a continuous extension, but omitting that, so S extends to the space of all convex bodies. So for any convex body, whatever its boundary is, it is possible to define sort of total mean curvature, integral of the mean curvature for its surface. And one should be careful here. So the curvature is not defined pointwise. The curvature is defined only as a measure. It is defined pointwise, of course, in the smooth case, but it is not defined pointwise here. So here the curvature is concentrated at the edges. And in the general case, for some arbitrary convex body, this will be some measure. So some measure whose integral is this function S, and which is continuous with respect to the Hausdorff metric on the space of all bodies. Yes? Yes. No, I mean it's continuous if you consider bodies inside a ball, so inside some bounded region. Because of course, if you take huge balls and take just a small step, then this will grow a lot. But one can write a bound on the change of the function quite easily in terms of the diameter of the body. Okay, so that's actually one of the most exciting things, I think. So so the discrete and the smooth worlds, so they meet and they generate something which is even bigger than both of them. I mean, so there are limits to this because this works very well in the convex case. So if the body is convex, then for some other sets which are not as good as convex bodies, so these curvatures as measures, they are not so well understood, and maybe it's impossible to define them in a good way. Okay, so that's I have 15 minutes, I think. Then I go to the next, and I have to go to the next part. Yeah, so here I have omitted some technical details, and actually maybe tomorrow I will. So tomorrow I was going to speak about some more concepts and methods of proof. And I mean, so Steiner did so these two classes. And it was Minkowski about 50 years later who then did so what I have written here. There's continuity and extension to arbitrary convex bodies. So now the third part, integral geometry. So I start with a question which doesn't seem to be related. So let us take a unit cube. So a cube with edge length 1. The question is, what is its average width? The average width of, well, the unit cube by Q. I mean, so that means we measure the cube in, so we squeeze it between two parallel planes, and that's the width in this direction, and now we take it at random. So that means we compute the integral over the one dimension, so over the circle, the length of the projection along the vector v of q. And we integrate with respect to v. But then since we are taking the average, we must also divide by the whole measure of the sphere, so divide by 4 pi. So projection, so this, if I have a vector v, and so here is my cube, then I'm projecting to, no, it's not over time, so I'm projecting onto v, right? I'm projecting on the line spanned by v. So I have some plane here, some plane here, and so plane that touches the cube here, the plane that touches the cube here, and then this length is what we are integrating. Good, so let us make it a sort of quiz. So it is clear that the minimum width is 1. And the maximum width, so when this distance becomes maximum, and what does it become? Square root of 3, right? Okay, so this is something between 1 and square root of 3. Maybe this is just the arithmetic mean. Or maybe this is square root of 2. Or maybe this is just 1.5. Because this is like 1.73. Or maybe this is by half, which is also lies very nicely between these two numbers. So you can choose your answer, and I will now state a theorem that provides the correct answer. Over S2, right. Yes, so of course I'm projecting, thank you, and then, yes, 4 pi is there. Thank you for the correction. So, the theorem. In fact, this average width it is proportional to the total mean curvature. Well, that probably eliminates this answer and also this answer. Although who knows, maybe the proportionality constant is something very weird. So the proportionality constant is that, so let me denote this by W of Q. So W of Q is this average width. For any convex body K, W of K is equal to 1 over 2 pi S of K. Right, S of K was this total mean curvature. And I mean, so usually it's difficult to remember the proportionality constants, but here one can check it just by taking K equal to the ball, the unit ball. Yeah, so the average width, this is like expectation, so expected length of projection. So you take an arbitrary line in the space and you project your cube onto this line. Or in other words, you take two planes which are orthogonal to your line and squeeze the cube between these two planes. So here the cube between two planes, and this segment is the projection of the cube then on the line span. And then I just take the usual expectation. No, so it's smaller than the diameter in any case, because in some directions the cube is smaller and in the other directions it is bigger. Good. So so which one is the correct answer? Somebody checked COD. So what was this S of K? this is 1/2 the sum of theta E L E. So all edges of the cube have unit length, all exterior angles are pi half, and there are 12 edges. And if you compute WK, then we must take 1/2 pi, and this is 12 divided by 8, and pi goes away, so this is the correct answer. The average width is 1.5. Actually, this can be a test if you are a rational person or irrational or transcendental. So one corollary of this theorem is that this total mean curvature is monotone under inclusion. So so it's inclusion monotone. That is if K1 is a subset of K2 and both are convex bodies, then S of K1 is smaller or equal than S of K2. This is not obvious from the definition that we have, because one definition is through the edges and angles, and who knows, this smaller subset probably maybe has more edges, and it's difficult to prove the inequality. Also in the smooth case, when we take just the integral of the mean curvature, so why a smaller surface, so which lies inside the other, why does it have a smaller integral of the mean curvature? So this is not obvious from the definition, but it is a direct corollary of this theorem. Good. So actually it's strict. Yes, if it is strict here, then it's also strict here, because yes, and equality here implies equality here. If you have a subset, then good. So I think, what can I do in 5 remaining minutes? I have an idea of the proof. On the other hand, okay, so let me state now a generalization of this theorem. So another theorem for today. So the coefficients in the Steiner polynomial, they have a similar meaning in all dimensions and for all k. So the coefficient at k in the Steiner polynomial K is proportional to the average volume of projections of K to subspaces of what dimension to d minus k dimensional. Minus k dimensional linear subspaces. So the coefficient at the term of order k, it comes from projections to d minus k dimensional linear subspaces. The exact proportionality coefficient is we one often writes the volume of so this of our neighborhood sum of k from 0 to d. D choose k wk of k times r to the power k. So this is just some normalization for the coefficients, and this wk of k wk of k this is beta d divided by beta d minus k times the integral of the volume of the projection of k, and the integral goes over all d minus, well, it depends. So I mean, we can take just all k-dimensional subspaces and project along k-dimensional subspaces. So this A is an element in the k-Grassmannian of D. So A is a k-dimensional subspace, and this PRA of k, this is projection to the orthogonal complement. Projection to the orthogonal complement of A. Beta is the volume of the ball, of the unit ball of the corresponding dimension. So beta k is the volume of the ball of dimension k. So that's, well, of course, here the integration goes along, so with respect to some measure on the Grassmannian, and which measure, well, so that is a very natural measure on the Grassmannian. This is the one which is rotation invariant and which has total mass 1. So this is rotation invariant, and the total mass of the Grassmannian is equal 1. So that means this integral is actually the average of the volumes of the projections, right? This W k is called by a very long German word. So this is the Kratmas integral. So this word consists of 3 parts. One of them, you know, quer means something like across, and mas means measure. So this is integral of across measures. So this is actually very the word which explains the definition very nicely. Okay, what is left? So what I did not tell today is there are special cases of this theorem. One of them is the Cauchy-Crofton formula. This is the case when we take k equal 1. So homework is to look at this formula. What does it say in the case k equal 1? And, well, dimension, any dimension. Already dimension 2 is interesting, and dimension 3 as well. And the proof of this, of the Cauchy-Crofton formula, is also very, very nice. So if you try to prove it for polytopes or for just 2-dimensional convex figures, so that's really something interesting. So very nice proof. then, well, that is a method how one goes from k equal 1 to all other k's. And in particular, here I have not proved so that this average width is proportional. I just stated the theorem. So to go from k equal 1 to the other case, that is some induction step, so which is also not very complicated, and that's a quite nice thing. And that's, I guess, more or less, I have to finish now, right?